In the previous video series, we had obtained from the Maxwell equations that light was an electromagnetic wave that traveled at 3 times 10 to the 8 meters per second. And at the time, I also observed that it was going to require that everybody agree, no matter how fast they're moving with respect to each other, would have to agree that any light waves they looked at, no matter where it was originating from, would have to travel at that speed, and that was going to eventually lead to E equals mc squared. That whole field that we are about to embark in is called Einstein's theory of special relativity. In this video here, I'm just going to start by setting the stage to show that we do need to have a rethink about Newtonian mechanics. So we'll start with just thinking about an electron gun. So remember, an electron gun, something looks like this. So what you'll do is you'll have a, let's see here, we'll have a negatively charged plate here. And then we'll have a positively charged plate with a hole in it over here. Then what you do is you run a very weak AC current through a filament, the sole purpose of which is to heat the filament up just enough to get a few electrons to jump off that filament. So some of those electrons will jump off the filament just because the filament is so hot. And they promptly are in an electric field, which means that they will start accelerating towards the positive plate. Now, most of them will strike that positive plate, but a very few of them will make it through these holes here and will be traveling at some speed. Let's call it v. So let's say that the potential difference that we have between our two plates here is 1,022,000 volts. And I know that seems like a very specific number, but just work with me here. How about you go ahead and pause the video for a moment and figure out how fast our electron would have to be going. You can do this by energy conservation. It's probably helpful if you remember that a way that you can write the mass of the electron is 511,000 eV per c squared. And let's just express our speed as a fraction of the speed of light. So go ahead, pause the video, give this a try, and when you're done, get back with me. All right. So we can go ahead and conserve energy here. So the kinetic energy of the particle as it leaves the electron gun, 1/2 mv squared, would have to be equal to its potential energy, which is it's going to be its charge, E, times the voltage difference through which it was accelerated. So we can solve this for the speed of our particle. So v is going to be the square root of 2e delta v over m. And the beauty of working in EVs, remember, is that they literally give you an E to cancel off against that E. So we don't have to substitute in any 1.6 times 10 to the negative 19s or anything. For the voltage, we will put in our 1,022,000 volts. And then we will divide by our mass of 511,000 eV per c squared. So what's going to happen here? Well, we're going to go ahead and be canceling the E in the unit here against this E for the charge of the electron. We'll cancel the volt there. So we're left with 1 over c squared, which was c squared, and then I'll be taking the square root of that. So we'll get something times c, but what will we get? Well, 1,022,000 is conveniently 2 times 511,000. So this is the square root of 4c squared. which means that we get that our calculated speed is 2c. This is a problem. There's absolutely nothing wrong with the calculation. The calculation is absolutely correct. However, this doesn't actually happen. If you attempt to accelerate an electron through a 1,022,000 volt difference, and you can totally do that using a device called a Cockcroft-Watson accelerator. The speed that you get experimentally, if you go ahead and accelerate through this voltage difference, is about 0.943 C. So this is what actually happens. So what does that mean? Well, we have ourselves a contradiction here. The theoretical calculation, using everything we know about the electricity and magnetism and Newtonian mechanics, totally predicts that we will be going at 2c. And when we measure it, it is absolutely not doing that. It's going at 0.943 C. So what this means is, just plain flat out, Newtonian mechanics is wrong. However, it can't be horrendously god-awful, because we've seen that it works incredibly well, say for doing things like throwing baseballs and stuff like that. So we'll be a little more charitable about it. Instead of saying it's flat out wrong, we'll say that's incomplete. Now, what we are going to need is a new model, a new physical model that will replace Newtonian mechanics. But we can't just up and do it willy-nilly. Newtonian mechanics was incredibly successful over a large range of problems. And so any new model that we come up with, we're going to have to show how Newtonian mechanics was a limiting case of this new model. This is a thing called the correspondence principle. So again, that just says that if you have a new model, it's got to line up with the old model where the old model worked. So perhaps an example that we can use to kind of wrap our head around this a little bit is to think about when we learned about planetary motion. So if you remember in elementary school, your teacher probably taught you that for a very long time, most people held that the Earth was at the center of the universe and that the sun orbited it. And so we would see the sun rise and set as it orbited us. And then your teacher probably said something like, boy, were they so stupid back then. We're so much smarter now. Now we go with the heliocentric model. Now, of course, a modern astronomer would go so far as where we put the sun at the center of the universe. And we have the Earth orbit around it. Now you have to have it orbit around the other way so that you can still get everything to match what you've seen. Now, in order to have the sun rise and set, you're also going to need the Earth to rotate around on its axis, but that's okay. So, first off, a quick note. The people who proposed the heliocentric model were not dumb. They were going with the best model that they could come up with. And there was actually a big objection to the heliocentric model that they just couldn't address. The ancient Greeks especially knew the Earth was a sphere. or very nearly a sphere, and they actually had a very accurate estimate for the size of the Earth based on the difference in shadows cast by sticks at different latitudes. They could figure out the angle between two cities by latitude, and if they knew that distance, they could work that out to figure out the distance, the diameter. Sorry, the circumference of the Earth. And they did this, and they got to within a few percent. So they knew that the Earth was a sphere. They knew that from looking at the shadow of the Earth on the Moon during a lunar eclipse, and they knew that roughly how big that sphere was. So they knew that the most natural way to explain how the sun would rise and set would be the heliocentric model, but the problem is you needed the Earth to rotate. And since they knew how big the Earth was, they could figure out how fast you would be moving on the surface of the Earth. And it turns out that the surface of the Earth has a pretty hefty tangential speed. And they realized that, so the objection that they had was that the winds would be so severe that it would just literally obliterate everything, that we shouldn't even be here. So even though it was computationally maybe a more convenient model, it was discarded in light of what they thought was the evidence. Now, of course, this is a story about the most dangerous assumptions that you can possibly make in science, which are the ones that you don't even realize you're making. In this case, the Greeks just tacitly assumed that the entire universe was full of air, which turned out not to be the case. It took people like Torricelli running up and down mountains with barometers to figure out that the thickness of the Earth's atmosphere was, for all practical purposes, the Earth almost doesn't have an atmosphere. If you're to shrink the Earth down to the size of an orange, the Earth's atmosphere is about the thickness of the orange part of the orange on the outside. And I'm not even talking about the nasty white stuff right under the surface there, just the orange bit right on the outside. So with an atmosphere that's that thin, it's easy for the atmosphere to rotate with the Earth, and thus the huge winds that the Greeks figured would happen weren't the case, removing the objection to the heliocentric model. But in any event, the issue that one of the other issues that you would have, and I want to be clear here, the geocentric model was incredibly accurate. But one of the issues that it had to deal with was the apparent motion of the planets in the sky. In fact, the word planet comes from a Greek word that can be roughly translated as wanderer. This is because every so often a planet will undergo something called retrograde motion. Now, every star, planet, everything will rise in the east and set in the west over a course of a night. But typically, night after night, if you map the position of a planet, you'll find that it moves a little bit to the west in the sky every night. Except when it doesn't. Every so often, it'll loop back and go the other way around for maybe a month or so, heading eastward in the night sky against the fixed stars before going back westward again. So this was a wandering kind of motion, so it picked up the name wanderer, which turned into planet in English. So the explanation in the geocentric model was to just plain say that the planets just plain physically moved backward from time to time. What they would do is they'd say as the planets were orbiting the Earth like so, they weren't actually orbiting right on this path right here. Instead, they were moving around in a circle around a point, and then that point was moving around. Every so often, the relative velocities would add up so that the planet was moving physically backwards against the night sky. And before you laugh at that, that model is insanely accurate. If you happen, of course, now most planetariums use digital projectors, which is a fairly new thing. But if you've had the opportunity to go into a planetarium that had a big electromechanical star ball in the middle, those actually use the geocentric model. Why? Because it's really stinking accurate. It's only when you're trying to get to the last few decimal places that things get really tough. Now, the heliocentric model it explains retrograde motion more naturally. Now, obviously, do not try this while operating a motor vehicle. But next time you are a passenger in a motor vehicle, if you fixate on the background while you're passing a car, you'll see that the car looks to be moving backwards. And that's exactly what's happening here. The Earth, say, passes Mars. And when you're doing that, Mars looks like it's going backwards against the sky. That's the retrograde motion. So it's a cleaner, nicer explanation for retrograde motion, but it has to explain star motion at least as well as the geocentric model. And here the correspondence principle can come into play. In the closest star other than our sun is over 4 light years away. It means it's going to take over 4 years for the light to get from there to here. So comparatively speaking, the distance between the Earth and the sun versus a star 4.2 light years away, and that's the close one, is pretty much negligible. And so it doesn't really matter whether you put yourself square in the center of the solar system or just a little bit off center moving around, it's going to look the same. So the geocentric model is a limiting case of the heliocentric model when you are looking at objects that are light years away. It just doesn't work as well when you're looking at things in our own backyard. So we need to have the same kind of thing happen for special relativity. We are going to need to require that special relativity converge to Newtonian mechanics when the speeds involved are much less than the speed of light. And believe it or not, pretty much everything that you have ever had any experience with fits that speed is much less than the speed of light. That's why Newtonian mechanics was so successful. Alrighty. So before we can start to think about how to replace Newtonian mechanics, which we'll lay more of the groundwork of that in the next video, I want to finish this video off by defining a term called an event and try to give some guidelines on how to think about them. So an event in physics is a coordinate quadruplet, x, y, z, and t. So it's where and when something happened. So usually it's helpful if you can imagine something happening at a specific time and place, and what I usually do is I imagine a firecracker going off. Other people imagine like a strobe light flashing or something like that. But whatever you think of, the whole point is it needs to be localized in space and time. So for instance, if I've got a firecracker going off here, Let's give it lots of pretty colors. That can be very well localized as happening at a specific position. Hey, that happened at x equals this, y equals this, z equals that. And the thing definitely blew up at a very specific time. So that's why I like kind of thinking about that. One of the other things we're going to have to be very careful about, a distinction we're going to have to be very careful making, is the difference between what you see and what you observe. And not all sciences, in a lot of sciences, these two terms are synonyms. They are not in physics. So you need to be a bit careful about that. So whenever I say see, especially in this treatment here, this is going to mean quite literally what you see with your eyes. And we can extend our eyes to things like video cameras, any kind of sensing equipment like that does the sort of thing that eyes do. So that's going to be talking about just all the light hitting a sensor and getting recorded at a specific time. That's what you see. What you observe will be different. This is what you conclude must have happened after you correct for speed of light delays. And although this is not something that comes super duper natural to us with light, because light goes so fast that near the surface of the earth you don't really notice how long it takes to propagate, this sort of thing does happen with sound, where we correct for it. So there is a beautiful description of how wide the Mississippi River is, due to Mark Twain. Mark Twain, in his book, the character is describing that there is somebody on one side of the Mississippi River who is splitting a log. And the log cracks and the sound propagates across the Mississippi River, which is a very wide river in North America. And a person on the other side of the Mississippi River, by the time they hear the wood split, they have already seen the axe get raised back over the head of the person splitting wood. So the Mississippi River is so wide, it takes a good long time for sound to propagate across. Now, it depends on the temperature, it depends on the pressure and all that, but roughly, the speed of sound is around 343 meters per second, give or take a bit. So, and this is also the same kind of thing that you do with sound again. Say when you see a lightning strike and you start counting the number of seconds until you hear the thunder to figure out how far away the lightning is. So roughly speaking, every 3 seconds you count off means that lightning flash happened about a kilometer away. So 3 seconds, 1 kilometer, 6 seconds, 2 kilometers, and so forth. If you insist on doing it in miles, it's about 5 seconds for a mile. So 5 seconds means the lightning flash was a mile away. 10 seconds means 2 miles away, so forth. Now, the light itself took time to travel from wherever it struck the Earth to wherever the lightning bolt struck the Earth to your eye. But since that's traveling at 3 times 10 to the 8 meters per second, over a few thousand meters, that just isn't anything to write home about, which is why we treat it nearly instantly. But the sound delay is a big enough deal that this is actually something the brain just sort of naturally does. It's got a way of kind of slipping the audio and video coming in between the ears versus the eyes in order to get the lips to appear to be going in sync, because it's actually enough that your ears can pick up on it. This is why, in fact, by just sheer happenstance, we got lucky when setting up television that we were using frequencies that were half the wall current. In most of the New World, in Japan, that's the 30 hertz, half of 60. And in most of the Old World, it's 25 hertz, half of 50. But either way, it turns out to be within that kind of slip time that the sound versus the image just kind of gets muzzled together in your brain and you correct for it. So we observe, so intuitively, we observe the sound when the sound must have happened, because our brain just automatically slips the video around to match the sound coming into our ears. Here, though, we're actually going to have to think about light propagating, but again, it's the same idea. Now, you can do literally this sort of a thing. You can say, hey, I was this far away. It took light a certain amount of time to travel to me. So if I subtract that time off, I can figure out when the event actually happened at the location where it happened. But I'll show you another picture that, at least when I learned this topic, it really helped me. So maybe it'll help you too. If not, go ahead and just think about doing the corrections, much like somebody watching a log get split, on the other side of the Mississippi. But what I like to think of is my picture of an observer is a whole bunch of clocks on an even lattice. Say like that. And the idea is going to be that we're just going to pre-correct for all the speed of light delays by pre-computing them all. So what we'll do is we'll imagine a really small person. Since I am part Irish, you'll probably hear me make reference to leprechauns occasionally. So I'll imagine all these little leprechauns sitting in front of each of these clocks. And then what we'll do is we will agree that the master clock located at the origin, at time 0 seconds, they are going to light off a firecracker there. And then the light from the firecracker is going to propagate out in all directions. Now let's say this leprechaun sitting over here is far enough away that it would take light a microsecond to travel. What they would have done is when this clock, because since this clock set off the light at t equals 0, this leprechaun would have already preset this clock to read 1 microsecond, like so. So would this one. So would this one over here. So would this one over here. And so then we'll assume that they have perfect reflexes. And so the instant that they see the flash of light, they start their clock. And the whole point is that since it took light a millionth of a second to get from here to here, this clock will be reading a millionth of a second, but so will the one at the origin here. So we've already accounted for the speed of light delay. Now, like this one here, this is going to be root 2 farther along than this. So like this leprechaun here would be presetting their clock to 1.4 times 10 to the negative 6 seconds. And same with the other leprechauns at the other corners. Oops. There we go. There. So all of our really small people sitting in front of each of these clocks will have their clocks pre-computed so that at the time the light pulse would pass, so this is a little farther away, it's going to take a little longer, but when they see the pulse, they'll set it to 1.4 times 10 to the negative 6 seconds, but then this clock will be reading that, and so will these here that had already been set a little earlier. So then all the clocks will be going all at once. So then, to make an observation, all that we need to have happen is we imagine this lattice is spaced finely enough that there is always a leprechaun with a clock wherever you need one. So a firecracker goes off somewhere, and the leprechaun will just send back a message to central control saying, "Hi, this is the leprechaun over at x equals 3 meters, y equals negative 7 meters, z equals plus 16 meters. At t equals 1.4 seconds, a firecracker went off right in front of me." So since the leprechaun was right there, there was no speed of light delay, and they correctly record the time. Now at some later time, other leprechauns would see the light flash, but they would correct for the speed of light propagation delay and conclude that the light flash did indeed happen at the time that the leprechaun who was right there stated it. So I think of an observer as this collection of a lattice of clocks. If you find that helpful, great. Otherwise, just go back to thinking about this and correcting for the delays, but instead of it being sound, it'll be light at 3 times 10 to the 8 meters per second. Alrighty, so in the next video we will review the Galilean transformation from mechanics, and we will see that the Maxwell equations in the Michelson-Morley experiment will demonstrate that there is a problem with it, and this will be our starting point for fixing Newtonian mechanics. So catch you over in the next video.